All right, and welcome to the first installment of Physics with Mr. Linscheid. Today what we're going to be talking about is free body diagrams and force equations. So I've got 6 different situations that I want to go through, and the first one is just a stationary object, meaning I've got a box sitting on the ground, it's not moving. And when we look at this situation, we want to be able to diagram the forces that are existing or being applied to that box. So the box is sitting on the ground, and that means that it must be being pulled toward the earth, and we call that the force of gravity, also known as the weight. Now, in addition to that force, I have a force that's keeping that box from going into the ground. The ground is holding it up, and that is called the normal force. Now, a lot of different situations will have different objects, and some of them are more complicated than others. This is pretty simple, but typically what we like to do is to represent our object with a dot, and that is what we call a free body. And then I just take those same forces that I had and attach them to the dot. So I've got my normal force and my weight pulling down. So that's pretty simple. Now, I can use this diagram to create what we call a force equation. And in this case, I want to sum up my forces, and to do that, I'm going to use the Greek letter sigma. And you've probably seen that in stats before, but that means the sum of. So the first thing I want to sum is the forces in the x direction. So the forces in the x direction, and I look at my diagram and I go, hey, there are no forces in that direction. So I'm just going to say that the sum of the forces here is 0 because there are no forces. In the y direction, it's going to be a little bit different story though, because now I have 2 forces. I have the normal force and I have gravity, weight. Now, do I add those together or do I subtract them? Well, they're going in opposite directions, so I'm going to have to subtract. Because the normal force is going up, I typically call that positive. Because weight is going down, I typically call that negative. So I'm going to subtract those two. I'm going to subtract the weight from the normal force. And then I want to know, what does that equal? Well, let's look at the box. The box is not moving. So that means it has an acceleration of 0. And remember that acceleration and force are basically married. If there is a net force, there will be an acceleration in the same direction. If there is no acceleration, there can be no net force. So that means there is no net force. These 2 forces are balancing each other out exactly. So these are my 2 force equations for the stationary object. Okay, well, let's make it a little bit more interesting now, and let's move over here and let's take a look at a box that is moving at a constant velocity. Alright, so we think, wow, something is going to be happening in the x direction here. So let's take a look again at what forces we have. Well, again, Earth is pulling down, so I have the force of gravity down. The Earth is pushing up to keep it from going through the ground, so that's the normal force again. And I have this object moving at a constant velocity. That means something must be pushing that object. And in that case, we're going to call that the applied force. I assume that the applied force is going to the right here because of my neat little motion arrows over here showing that it's moving to the right. Well, if it's moving at a constant velocity, that means the acceleration is 0. Well, how can I have an acceleration of 0 if I have a force here? What this means is there must be another force going backward. And in this case, because it's on the ground, there is the force of friction. And because it's moving, it is the force of kinetic friction. So to put this into a free body diagram, again, I just represent my box with a dot. I go normal force, weight, applied force, and friction again. Now I want to sum up my forces. So in the x direction, I have the applied force, and I have the friction force. And again, because they are in opposite directions, I have to subtract, and because the applied force is going to the right, I'm going to just call that positive and friction negative. And there is no acceleration, so that means there cannot be a net force. So that's my equation in the x direction. In the y direction, it's the same as it was for the previous situation. I have the normal force, and I'm going to subtract the weight because it's going in the opposite direction, and because, again, there is no acceleration downward or upward, there is no net force. So in this case, it's going to be 0. All right, let's move on. Now let's say this box isn't moving at a constant velocity, but now it's moving faster and faster. So it's accelerating, and we're going to say that it's accelerating to the right. So it has a positive acceleration. All right, well, let me look at what forces I have. Again, normal force, weight. There must be some applied force here. And I have the force of friction, but this time the force of friction is less than the applied force. The applied force must be greater in order to have an acceleration and a net force going in that same direction. So let me put that onto a free body diagram. Normal force, weight, applied force, and friction. Now here are my equations. I sum up the forces in the x direction. Well, in the x direction I have the applied force, once again just like the previous problem, and I have friction. And because they're in opposite directions, I subtract. And they are not equal to 0 this time. Why? Because there is an acceleration, so there must be some net force. Well, we don't have any numbers to go with this, but I'm going to give you a little bonus knowledge here. This is Newton's second law. The net force is equal to the mass of that object times the acceleration in the x direction. So this is my equation. In the y direction, it is no different from the previous two. There's nothing happening other than a lack of acceleration in the y direction. So I have the normal force minus the force of gravity equal to 0 once again. All right, moving right along. Let's take a look at an object now that's coasting. So nobody's pushing this object, it's just somebody gave it a push maybe at one time, but now it's coasting and it's probably going to come to a stop. So what forces do we have on this object? We have the normal force, we have weight, and because it's going to come to a stop, we have friction, which is taking away its speed. It's accelerating in the negative direction now, so I have a negative acceleration here. For a free body diagram, normal force, weight, and friction. So let's sum up those forces. In the x direction, I have only one force this time. I have the force of kinetic friction. And I know that it's accelerating in the negative direction, so it does not have an acceleration of 0. Therefore, there must be some net force, which again I will set equal to max. And when I figure that out, I'm going to find a positive acceleration. So that, or I'm sorry, a negative acceleration. In order for that to end up negative, my force here must be negative as well. We have chosen left to be negative. So any force in that direction must be negative as well, or at least subtracted. In the y direction, I have exactly the same thing that I did before. All right, a couple more situations here. Let's take a look at an object that's in free fall. Remember, the definition of free fall is that there is no air resistance, and the only force acting on an object in free fall is gravity. So I have the force of gravity pulling down, and that's it. My free body diagram is really simple. So that's it. In the x direction, again, there will be no forces. In the y direction, I only have one force. Down, I typically, again, consider it to be negative. So I'm going to say the sum of the forces is negative F sub g, which will equal ma y this time. And the last situation, I have an object falling at terminal velocity. Well, what's terminal velocity again? Terminal velocity is an object that is not accelerating. So basically we have an acceleration of 0. The force of air resistance this time. There is no normal force because it's in the air, it's not contacting the surface, and the force of gravity. There are no forces in the x direction, and in the y direction we have two forces. We have, again, the force of air resistance, and I'm going to subtract the force of weight or gravity. And that will be 0 because acceleration was 0. So there you have it, free body diagrams and force equations. Peace.